Hey everyone, so today we are going to talk about improper integrals. Okay, so what are improper integrals? So one of the classification of integral is the definite integral and the indefinite integral that you have already seen. So definite means the limits are there and indefinite means limits are not there. So that is one classification. There is one more classification of integrals which is nothing but the proper integral and the improper integrals. So one is proper and one is improper integral. So which integrals come under this category, and the question is which integrals comes under this category. That's what we are going to see today. Okay, now what are proper integrals? Now suppose a domain is a bounded domain and you take your function to be a continuous function. Okay, so we know that integral of a function from a to b f of x dx exists. Then such kind of functions we say, or such kind of integrals we say they are proper integral, because you can apply the Riemann theory. Okay, so or actually if I want to generalize more, if I want to remove the continuity, actually why I want continuity, because I know the continuous function over closed and bounded interval is always, it will always give me the finite values. Okay, because it has maxima minima and at all the points I will have finite values. So I have finiteness over here. So if I have the finiteness over here, then I can apply Riemann theory, not a problem. And I can see whether the integral exists or does not exist. If you want existence of integral, then you can take continuous function over close AB, or you can take discontinuous function, but it should be discontinuous at finitely many points. Or in general, Riemann proved that if a function is discontinuous at countably many points, means you can count, then also the integral exists. Okay, so if you have a closed and bounded interval and the function is taking the finite values everywhere, then such types of integral comes under proper integral. Okay, so that is one thing. But now suppose the domain becomes unbounded, then what is the scenario? Suppose if I give you 1 comma infinity, or if I give you minus infinity comma say 4, or if I give you minus infinity comma infinity. Now here the domain is unbounded. So question is whether its integration exists if I go by this Riemann theory. Well, you can't apply Riemann theory to such domain. I will tell you why. But even before that, you might think, hey Jatin, why we are looking for unbounded domain? If the domain is unbounded, then if I integrate, then won't the integration be infinite? No, that need not be the case. So for example, if I give you this as a function e raised to minus x dx, if you integrate this over this domain, your answer will come out to be finite number. Okay, so if the domain is unbounded for some function, you can't simply say, okay, the integration, the area under the curve is also infinite. No, area under the curve can be finite. And my suggestion is you please solve this example. In the next lecture, I will solve this example properly so that you will realize the 1 or 2 mistakes that I feel you will do while solving this problem. Okay, so make sure you solve and tell me what is the answer in the comment section. Okay, so that is the first thing. So, and you can see what is the graph of e raised to minus x. E raised to x is like this. So e raised to minus x will be like this. It will never touch the x-axis. It's the asymptote. And now when you take 1 to infinity, this area, okay, you can see the distance keeps on decreasing, so this area comes out to be finite. So if the domain is unbounded, you cannot say the integration has to be infinite. Area under the curve is infinite. Okay, so we have this example. So now the question is, why can't we apply Riemann theory to unbounded domains? Okay, what's the problem with unbounded domains? So the problem is, see, whenever you have a domain, what is the first thing you do? You do the partition of the domain, right? You do the partition. That's what Riemann said. How you do the partition? You call this your left end point as x0, then you call somewhere as x1, then someone as x2, and you keep on going xn minus 1. But now the question is, there is no right end point. It is going towards infinity. Question is what will be your xn? You don't have right end point, so you won't have the last end point over here. That means you can't partition the domain. Okay, so that's the problem. You can't apply Riemann theory. But some may say that okay sir, even if we can't give the endpoint, what if I take this as the first subinterval, this is the second subinterval, this is the third subinterval, this is one subinterval, and the last subinterval you take is from xn minus 1 to infinite. So your whole interval is the union of this plus this, union this, union this, union this, and union xn minus 1 to infinite. Then the whole interval is union of these intervals. So it's also partitioning the interval. So what's the problem? But then the problem is when you apply the Riemann theory to this infinite subinterval, what you are doing? You are taking the value of the function into the length of the subinterval. So what will be the length of the last subinterval? It will be infinite. And then you will say, oh, the length is infinite, Riemann sum is infinite, hence integral does not exist. But is that true for all integrals? No. I just now wrote 1 to infinity e raised to minus x dx. Okay. So therefore, as soon as you have an unbounded domain, you cannot apply Riemann theory because problem arises in the partitioning the domain itself. Okay. So since we cannot apply Riemann theory, therefore we are not putting integrals over this domain under the category of proper integrals. Therefore we are having another category which is improper integral. So whenever you are having a continuous function and the domain is unbounded, then we say those integrals to be the improper integral of type 1. Okay. Whether that integral exists or does not exist, I don't care. But whenever you have a continuous function over unbounded domain, we say that it's an improper integral of type 1. Yeah, there's one more thing. Like for e raised to minus x, integration was existing. Integration did not always exist. You take integration 1 to infinity x dx. Okay, this is infinite. So, but yeah, it need not always be infinite. So yeah, so that's the first type in improper integral, type 1. Function is continuous but the domain is unbounded. Let's come to the second scenario. Suppose your domain is bounded. Suppose your domain is bounded, but at some point C, suppose at some point the value of the function is infinite, plus infinite or suppose minus infinite. Then again you can't apply Riemann theory. Why so? Because now say the domain is bounded, so no problem in partitioning the domain. You can call this as x0, x1, x2, xi. Somewhere here you have C. Let me call this as x3, and this is my xn. So no problem in partitioning the domain. Now what is the next thing you do? You take the length of the subinterval into the value of the function. So you get the rectangle. Now when you are in this this subinterval, this is the length of the subinterval. But what is the maximum value of the function? We know that at C it is taking infinite value. Okay, so like if you have function 1 upon x minus c, at C this is taking infinite value. So when you are in this subinterval, the maximum value of the C is infinite. That means it does not exist. Okay, so in that case your upper sum will be infinite. As soon as upper sum comes out to be infinite, your integral become infinite. But is that always the case? Answer is no. If you take, suppose if you take 0 to 1 upon root x dx. Okay, you take this integral and you try to solve this. Okay, now you can see what is the function. Your function is 1 upon root x. What is the interval? 0 to 1. Domain bounded? Yes. But is the function taking finite value at all the interval, at all the points in the interval? Answer is no. At 0 it is infinite. But you will see that the answer is coming out to be finite. Okay, yeah, this is the second homework. So you have to tell me what is the answer. I want you to solve this because I will tell you the proper way to solve maybe in the next lecture. Okay, so yeah, so when a function is taking infinite value or suppose minus infinite, then lower sum will create the problem. So if the domain is bounded but at some point function is taking the value plus or minus infinity, then again you cannot apply Riemann theory. Okay, therefore, but that does not conclude that the integral does not exist. We do have integrals which exist. Okay, so therefore this type of functions or this types of integrals, which type function is continuous but at some point in the domain it's taking plus or minus infinity, then if you are integrating such functions, then we call it as an improper integral of type 2. So this is the classification of improper integrals, or I will say integrals and improper integrals. Okay, so you can remember this tree diagram, which will help you to make sure the concept will be clear. So proper and improper integral, and here again you have type 1 and type 2. What is type 1? Your domain is unbounded and your function is continuous. What is type 2? Your domain is bounded, so no problem in partitioning, but function is taking in fact plus or minus infinity at some point. Then this is type 2. So yeah, that's about improper integrals. So now in the next lecture we will take examples on type 1 and type 2. So I hope this idea is clear. If you have any doubt, you can ask me in the comment section, and if everything is clear, then do not forget to like, share and subscribe. Thank you.